I'm joining you from the unofficial Rwanda satellite event, and you might be wondering, why are you not at ICML? We're all here. It's because I am at the African Computer Vision Summer School in Kigali in Rwanda, and I'm going to be teaching about vision and language models tomorrow, and it was simply impossible for me to be in both places at the same time. I would have loved to be there. I'm happy to continue any discussions after this over email. I heard there's a Discord server. You've all mentioned this. I don't know what it's about. If it's about tokenization, I want in on that too. But today I am going to talk about creating high quality NLP tools for all written languages. That's the main thrust and the drive throughout this talk. And the main problem stems from the fact that NLP is an open vocabulary task. There are 3,000 written languages in the world, and 400 of them have more than 1 million speakers. But NLP usually covers 100 languages due to their size of their Wikipedias back in about 2017. And this, I think, results in technological exclusion for billions of people. The way that we try to overcome this open vocabulary problem is either by training a vocabulary or estimating a vocabulary over a corpus using something like byte pair encoding, where we also might encode unseen tokens using byte level backoff. There are other algorithms for estimating this vocabulary, and Yuval covered them really nicely in his talk. And there's also an emerging approach for corpus-independent approaches based on characters or bytes, where a new challenge appears where we have to deal with longer input sequences. And taken together, this results in what we call the vocabulary bottleneck. The vocabulary bottleneck is something that exists in two locations in a language model. There's a representational bottleneck in the embedding layer. So just after you have tokenized it and you look for those entries in your embedding matrix. And there's also a bottleneck in the output layer where if you want to support really hundreds of thousands or millions of items in your vocabulary, you're usually going to encounter a computational problem because you have this normalizing constant over all the words in the vocabulary. And so you can ask yourself, where's the sweet spot along this axis of long sequence lengths to large vocabularies? And I've highlighted a few different approaches here. That's not to say it's all of them. But if you want to cover every possible written language and you want to do it using machine information, you might approach it by using something like bytes. Some languages will be poorly encoded by bytes using, I think, maybe 4 bytes per character. But you want to cover everything that's possible there. Then we can look at approaches that are based on characters or UTF code points. We could also maybe look at models with a small subword vocabulary like BERT, or maybe a much larger subword vocabulary like XLM Roberta. And at the very extreme here, where I think we have the largest vocabulary that I can remember seeing, was the original word-to-vec algorithm, which had 3 million entries in its embedding matrix. And so every possible variation of words, capitalized, uncapitalized, weird small spelling mistake in the middle of it, all of these were individual entries. And I want to talk to you today about an alternative. And this alternative is treating language as vision instead of a set of discrete inputs. So on the left-hand side here, I have the traditional NLP pipeline, where you start with some raw text on disk, and then you go through a sequence of steps, including normalization, where you might split out punctuation from surrounding words, or maybe you lowercase some of the words if that's the intended target of your application. Then you'll tokenize the text using one of the methods I described previously. After that, you have an embedding lookup, which is going to be some kind of word matrix. And then at the end of it, you model this, either by putting it through a transformer or through a recurrent neural network, if you're into that type of thing. Instead, what I'm going to talk about is a different vision where we throw away everything in between the raw text and the model, and we replace it by one step, where we render the text as an image. And so what this looks like is something that I'm showing over here. This is an example for Amharic. The sequence at the top, I believe, reads that Ethiopia is a country in East Africa. If there are any Amharic speakers in the audience, please write me a message to correct me on that. Underneath this, we have the rendered version of this from our pixel encoder. And this is then randomly masked, which is the input to a model that tries to reconstruct that data while pre-training for the purpose of trying to learn a good model of text without having to deal with the normalization, tokenization, and embedding lookup steps that are typically fixed processes in our model pipeline. So how did we come to this model? How did we get here? I was inspired by three pieces of work. The first was by Liz Selesky, who I guess is maybe in the audience. Liz was very inspirational to me on this. She had a paper in 2021 on robust open vocabulary translation from visual text representations, or VisReps. And this was a super exciting approach to training a machine translation model where the text was rendered into an image, as shown on the left, and then a stack of convolution layers with a sliding window operated over this input to provide the inputs to an encoder, and then this was subsequently fed into a standard tokenization-based decoder for machine translation. And I thought this was super cool to see that you could learn a translation model using these visual representations. A really exciting work. The second piece of inspiration appeared in the same year. This was masked autoencoders, or scalable visual learners. The idea here was that you take an input image, split it into patches. This was already happening with vision transformers anyway. And then you would randomly mask about 80% of the patches in the input, and then train a decoder to reconstruct those masked patches using a pixel level loss. And this was done without any label supervision at all. And so it inspired me to think, if you can do this for visual recognition of really complex RGB data, why can't you do this for language? The third piece of inspiration was also from 2021. So as you can see, this was a year where I read a lot of papers and felt really inspired. Page 38 of the appendix of Learning Transferable Visual Models from Natural Language Supervision has an experiment on sentiment classification on the SST dataset from GLUE, where the researchers at OpenAI rendered the sentences from SST into an image and found that you could fine tune this to get acceptable performance. I mean, it's still 10 points short of BERT, but it was okay. You could learn something. And so you do this by learning a contrastive image text supervision model, which is still giving the model a lot of information about what text looks like. And so the combination of these three papers inspired me to think about what could we do by just treating language as raw pixel data and trying to learn everything directly from that. Today, I'm going to talk about 4 projects in this direction. The first is presenting the pixel language model itself. Then I'm going to speak about some efforts on improving the text rendering strategies in the inputs to the model. Then I'll talk about some recent work on going multilingual in our pre-training. And I'll finish up by talking about an application to historical document processing. This first part of the talk was presented at iClear in 2023. I'm just going to dive straight into the model. So a pixel language model starts with a collection of text on disk or in an arrow file, like this example shown here. And then we render this text into an image using open source rendering library called Pango Cairo. We use open source fonts from Google Noto, which supports hundreds of different writing scripts. And then we draw this into 16 by 16 pixel patches with a completely unconstrained flow, as you can see here from left to right. Words cross over patch boundaries. Sometimes we draw in all kinds of information that is just no control here whatsoever. Then we project this through a convolution layer and add in positional information. And then we randomly span masks of the input patches with the hope that this will help the model to learn consecutive sequences of patches in the input. This is then, the unmasked patches are then the input to a 12-layer transformer encoder. And then an eighth layer transformer decoder is trying to reconstruct the patches, and in particular the pixels that were not observed in the encoder. And so if you know about language models like BERT, which everyone here does, it's really similar to some of these ideas, except we don't have a linear layer that decodes into a softmax. We have a transformer that decodes into pixel space. So let's talk about some of the different parts of the model. We have a very flexible text renderer. It can render full RGB data, including emojis. We can handle left to right and right to left writing systems. We can also deal with word level rendering when we want to apply it to a task that would benefit from knowing word boundaries. So for example, dependency parsing or part of speech tagging. Another thing that is quite good to know is that the rendered text is compact. It doesn't inflate sequence lengths. And so pixel encodings produce sequences that are at least as long as BERT. And so what I'm showing here on the right-hand side, this is from the universal dependencies dataset, where we have human reference segmentations for all of the instances in that dataset. This one is Turkish. And we can see here in the yellow line, this is the length on tokens of the Turkish input data. And then in the purple line, we can see the pixel one, and it's matching mbert quite well. The y-axis is the proportion of the text that's encoded as either k subwords or k patches. And if we take this and then we expand it out to look at 9 different languages, this is where we can see that there's no obvious length penalty being paid here. In fact, for Arabic, we can get sequences that are shorter than other approaches. We can see for English, it's not quite as effective, that's in the top right, as BERT or mbert, but BERT in particular has a tokenizer well optimized to working with English text. One kind of standard example here is Korean in the bottom left. So BERT is really good at tokenizing Korean, but it's a bit of a trick because Korean by BERT is almost all entirely uncs. And so it's not really doing a good job. It's just producing really unuseful sequences. And so with this rendering strategy, there's no length penalty. And that's, I think, a really nice a property of this. And unlike for some LLMs, which was highlighted by Ahia and colleagues in 2023. Another aspect to look at is the embedding layer in the model. So like I said, we render the text, and then our embedding layer is a convolution layer, where our input patch is 16 by 16 by RGB, so by 3 as an input. And then we have 768 kernels, which have exactly the same size and dimension. And so what's happening here is that each of these kernels is kind of taking a snapshot of each patch. And so then we do this simultaneously for all of the inputs. These are not learning cross representations. There's no sliding window here, but it's giving us this kind of initial snapshot. And on this next slide, I have an animation of the evolution of the convolution weights during pre-training. It might not look like this image is changing, and if my internet connection isn't great, it won't look like it either, but I'm going to try and highlight what we're seeing here. So this is for all 768 kernels, from the start of pre-training until the end. The patches I'm highlighting here in pink, these are ones where it's learning about the presence or absence of any pixel data in the input. So they're either almost completely black or almost completely yellow. There are many different kernels that are capturing horizontal strokes throughout the inputs. This could be because of the properties of the English language data we're using, or perhaps the rendering strategy we have. And there are a few of these kernels that capture curved shapes. This could be, once again, because we have the unconstrained rendering. And so it's capturing that B's and C's and E's and G's sometimes overlap in between different patches. Nevertheless, we can see some properties of the language data might be captured within this. And finally, in terms of the objective function, like I said, we have the outputs of the transformer encoder. They go into a transformer decoder stack. Then we have a layer norm and a linear projection into 16 by 16 by RGB space. And from this, we train the model with mean squared error objective over the randomly masked patches. There's no softmax normalization anywhere here. And the model is just trying to reconstruct everything at the pixel level. So we end up with a new type of generative model of language based on pixels. Here I'm showing the evolution of reconstructing text while the model is being trained. This is an unseen document about penguins and the design of their knees. And so in blue here, I'm showing cherry-picked examples of where the model improves the quality of its reconstructions at the pixel level. So on the bottom, we can see that by the final 1 million steps, the model can fill in from context that this is giving an illusion of something, whereas at the earlier step at 100,000, there's a real mess of it overwriting many different pixel words at the same time. The red examples are the lemons, where we can see for some completions, the model just cannot get a good grasp over what's missing inside of that. So going on to talk about pre-training, for our first model, we pre-trained it on only English data, on the English Wikipedia and the books corpus, so this mirrored the pre-training of BERT. We trained it with a sequence length of 529 patches. And like I said before, it's not a wasteful representation compared to using something like BERT. It took 8 days on 8 A100s, but more recently we managed to get this down to 2 days on 8 A100s. And the model is really small compared to what people are using today. It has 86 million parameters in its encoder. And there is a trace of non-English text in the pre-training data for the English Wikipedia and books corpus as estimated by Blevins and Zettelmeier. And that trace is going to appear in, for example, in Wikipedia articles where you might see traditional Chinese and simplified Chinese in pinyin alongside the name of the article topic. In terms of downstream tasks, we evaluated this model on universal dependencies, Masaka NER, GLUE, and the zero benchmark. We compared it against two models. The BERT-based model, because it uses pretty much the same pre-training setup, the models are almost identically sized. We trained it for the same number of steps on the same data. We also compare it against Canine C, which is trying to solve exactly the same problem as we were trying to solve using UTF-32 code points. The model has larger capacity in terms of its parameter size, and it's pre-trained over more languages, in this case 104 languages. If we look at the results for dependency parsing, the first thing I want to highlight here along the x-axis is, in comparison to BERT, which is trained on the same data, the unknown tokenizer rate is the unknown token rate from the BERT tokenizer is a good indication of the performance gap you'll get for pixel representations. So for Coptic, Korean, Tamil, and simplified Chinese, the gaps here are really quite substantial. And I think at the time, this was a state-of-the-art result on Coptic dependency parsing. We couldn't find anybody actually working on dependency parsing in this data set. I think that might be because there just weren't the resources to pre-train or fine-tune models for them to be good enough. And so the main takeaway from this, the main insight here is that Pixel can vastly outperform BERT on unseen scripts. That's a little bit easy. If we move on to named entity recognition in the Masaka NER dataset, here I'm now comparing BERT versus Canine versus Pixel. So the first thing I want to highlight is that on the only non-Latin script, Pixel, which is pre-trained on one language, outperforms Canine, which is pre-trained on 104 languages. BERT completely fails on Amharic, which is related to what I was talking about earlier when I was motivating the whole idea of treating language as vision. For the rest of the languages which are in Latin script, here Pixel also outperforms the multilingually pre-trained Canine C in almost all cases, but it doesn't perform as well as BERT with its Latin script dominance in the tokenization that it has. If we move on to sentence level understanding with the GLUE benchmark, Pixel is outperformed by BERT in all of these tasks, suggesting that maybe there's something about the local level objectives in pixel reconstruction that are not so useful for sentence level tasks. And also that the English tokenization that we get from BERT is really good and useful for these types of sentence level understanding tasks. Finally, we also investigated how Pixel deals with orthographic text attacks in the zero benchmark. So these can be where the sentence is perturbed into confusable characters or inner shuffles, or taking a phonetic reading of the sentence instead of using the words that were originally written with no attack. And when we look at this on the SNLI dataset, Pixel here is shown in blue compared to BERT, which is shown in yellow. I want to highlight up here in the top left for confusable characters, we can see that Pixel can deal with up to 80% attacks much better than the BERT model can. And for something like phonetic attacks, where you replace the words with their phonetic readings, we can see here Pixel is also more resilient. And I think this is because the model is moving into non-canonical and unexpected tokenizations of words. And it's hard for the transformer language model to perform a good composition function over those inputs that it's rarely seen. And so after we finished working on this project, we realized we had made some pretty silly mistakes in our rendering of the text. This led to a follow-up paper in the same year at EMNLP. And so our original text renderer produces many nearly identical patches. Here you can see the 10 most frequently occurring patches if you do unconstrained rendering. And they have one thing in common: they are the same word with a small X dimension shift. So this is representation and compute wasteful in some of the worst ways. We don't have a lot of data if we're working with English Wikipedia and the books corpus, and we are making the model learn, I think, kind of not useful variances across the inputs. So the question we had was, can we do better than this? So we devised a set of different rendering strategies. So the first one here was the continuous rendering, which I've already criticized on the previous slide. The second is a structured rendering approach based on character bigrams, where each character bigram starts in its own patch. So we can see here that the sequence length increases slightly compared to the continuous setting, but we're essentially defining a vocabulary or an inventory over what possible patches can appear. And this inventory has a space in the billions or maybe tens of billions, because we can fit almost everything into this. We don't need to worry about softmax output layers and embedding matrix sizes. Another alternative is we can deal with structured rendering based on monospaced fonts. This is not a really good idea, because there are lots of languages that will not deal well with monospaced fonts. They don't handle this at all. So for example, Arabic is just going to completely break if we try to do this. And the final option is to deal with structured rendering based on words, where each word must start at the start of its own patch. And this way you can think about learning some regularities about the starts of words, but then after that, things become a little bit more free-spirited. And so when we investigated the number of unique patches that we found after processing just 10,000 sentences from our data sets, in purple here, we can see the continuous strategy was just a complete disaster. The blue dot dashed line here, this is for word-based rendering, it grows much more respectfully. Whereas the bigrams in mono are really quite small in terms of the unique patches. So we ended up choosing the bigrams rendering strategy for this approach. And we pre-trained a pixel language model using exactly the same data, the same hyperparameters, but just a slightly different rendering strategy. And then fine-tuned it, for example, again, on the glue data set. In this case, what I'm showing here in the orange bar is that with bitext rendering, this is another insight I want to highlight in this talk. The bigram text rendering produces much better pixel language models. In this case, it was for a sentence level processing task that we performed really poorly on with the unconstrained continuous rendering strategy. And in some of these instances, we're really within about 1% of the performance of BERT on exactly the same data, except for COLA, which has become kind of massive problem for everyone forever. Another thing that we explored in this paper, and I'm really quite excited about, is scaling down language models. I think that, when we're building tokenization-free language models, we can think a little bit about who we're building them for. And having small models is going to be useful for so many people in so many different contexts. And with better text rendering strategies, we can create really effective models at smaller scales. So here I'm showing the averaged performance across the collection of dependency parsing datasets, all of the glue benchmark, and the tie-dye QA question answering dataset. The teal, blue, green colored bar is for the base model of Pixel. The orange is for the bigrams, showing we got that improvement at exactly the same parameterization. And then we can go down to 22 million parameters in the model in the dark blue and retain most of the performance across all of the tasks. Or we can even squeeze things down to 5 million parameters. We lose a bit here on tie-dye QA and glue, but for parsing a word level task, it performs quite competitively. And I want to highlight here that these are not distilled models. This is trained from scratch at 5 or 22 million parameters. And all of this, I think, is an exciting direction for future research of going much smaller than 1 or 3 or 8 billion parameters. Most recently, we have been exploring the ideas around multilingual pre-training. And so I said that the models I spoke about in the first two parts of this talk were trained only on the English Wikipedia and the books corpus. In the middle of May, we pre-printed a paper on multilingual pre-training for Pixel language models. This is a model that we call M4. It's a multilingual model trained on 4 languages. It has exactly the same architecture and hyperparameters as pixel bigrams. We chose this because we want to do controlled, careful experiments. In this case, our variable that we were manipulating was the languages the model was exposed to. And instead of only exposing it to English data, we trained it on 4 visually diverse scripts sourced from MC4. So we have Latin, in this case English, Han, in this case simplified Chinese, Cyrillic, we have Ukrainian data, and Brahmic, we use Hindi data. And these languages are almost perfectly balanced throughout our pre-training. The sentences are not aligned in any way, so it's always learning from different examples. And within a mini batch, it's seeing completely different languages. The masking is different across the different instances. And so what we were hoping is that the M4 model would not be able to learn language-specific subspaces within the transformer, since there was no obvious signal about where or when it was going to see one of these 4 languages. In terms of evaluating it, we then had a problem of how do we test this? We've now trained on 4 languages and we want to see, does this give us a much better model? We turned to the SIB200 dataset for text classification. This is a really cool dataset. It's a 200-way parallel dataset where you can fine-tune models for classification, or you can just do zero-shot prompting if you have a model that allows for that. I'm going to show the performance of 3 models here. So the Pixel BGS is the bigrams model, trained only on English. M4 is our multilingual model, and Canine is the model I've been comparing against that uses UTF-32 code points. I'm going to step through the results kind of slowly so that we can take them in. The first set of results here are for Arabic script languages. So we have Egyptian Standard Arabic, Uyghur, and Urdu. We can see that Canine has a real big edge here for Egyptian Standard Arabic, but for Uyghur, it's really no difference between M4 and Canine. For Urdu, once again, there is a big difference there. But that's a good first start there for the M4 model, given that it wasn't pre-trained on any Arabic script data. In terms of the Brahmic scripts, so now I have a star symbol to show that we pre-trained on Hindi. And for that one, the Pixel M4 model performs really well on SIB200 classification. But it also performs much better than the Pixel bigrams model for Tibetan and Bengali and Tamil and Telugu. And in all cases, except for Tibetan, it outperforms Canine. even though it was only pre-trained on Hindi. So we're probably getting some really nice positive language transfer here based on the writing scripts. If we move to the Cyrillic scripts, what we can see here is Pixel was pre-trained on Ukrainian, and this benefit of the pre-training transfers really nicely into Russian and Kyrgyz. It's really outperforming the English-only biograms, and for Ukrainian, we can outperform Kanin as well, probably because we've seen more Ukrainian data than they have from Wikipedia. If we look at the Latin scripts, the story becomes a bit more confusing. So Pixel biograms was pre-trained on this. The Pixel M4 was pre-trained on English. And for that, we don't really see any difference in performance for English. For German, we get a small difference in performance, and the same for Finnish. But for French and for Turkish and for Uzbek, we don't really see anything there. And so there might be something here with we're pre-training the model in English, which is a Germanic language. And if we try to evaluate it outside of Germanic languages, maybe there's something that the model is learning during pre-training that's specialized towards that. And that's worthy of some more investigation. For the CJK, Chinese, Japanese, and Korean, pre-training on Chinese gives really nice improvements for Japanese and Korean. And finally, we added in a collection of languages, Greek, Hebrew, and Armenian. We added in Hebrew because a Hebrew speaker once told me that this will never, ever work for Hebrew. And I guess compared to Kanin, it doesn't work as well, but we do get some improvement from pre-training on unrelated scripts in that direction. So the main takeaway from this is that the multilingual pre-training we've done here seems to be very helpful for sentence classification in SIP 200. If we look at something like dependency parsing, which is a recurring theme through our evaluations, multilingual pre-training here also helps, but it's more exclusively for the non-Latin script languages. We do seem to be getting into this kind of bottleneck or this plateau of Latin script processing, and that's something we need to investigate a bit further. We also wanted to investigate and understand how or what type of mechanism might be leading to better performance here. So we wanted to look at this from the perspective of zero-shot sentence retrieval, where we encode sentences using SIP 200 that are not trained on at all, and we measure the cosine similarity between the encoded datas in the 4 different pre-training languages. And what we find here is that multilingual pre-training does lead to better so-called semantic representations of the text, but performance seems to be biased towards retrieval into English performing best, and this performance coming at the end of the transformer stack in our encoder. There's a lot more work to do in this direction. The final thing I want to talk about today is an application to historical document processing. This part of the talk will contain data samples with racist text. They'll be shown in orange, so if you don't want to look at them, you can just ignore the orange areas. Historical document processing is a huge area of research for digital humanities researchers and historians. The typical process for working with historical documents is to scan them into high-quality digital formats, perform a one-off OCR process that may or may not be good, and then use those OCR annotations to search through the documents for what you're looking for. The main question we had is, can we do this without OCR? We collaborated with researchers on a collection of Caribbean newspapers, and they were interested in tracking articles about escaped slaves. They wanted to collect data about the given name for escaped slaves, the rewards offered, the contact person, among many other types of questions. We have a data set of 1.5 or 1.6 million scanned pages, so it's a lot to work with for pre-training. The researchers who led this project designed a new pre-training strategy called historical document-aware pre-training, where they had a mixture of scanned newspapers and synthetic newspaper-like text, where this newspaper-like text was produced by randomizing the fonts within different blocks, rotating the text, and adding in salt and pepper noise throughout the input. The model was then fine-tuned for VQA on the newspapers, where the question was rendered into the canvas and then the newspaper clipping was rendered. And we trained the model to annotate the context of the correct answer. When we evaluate this model, what we found was a surprisingly good performance compared to a model that was trained on manually transcribed text, which I think is a really high bar to beat, where you have professional historians transcribing these documents. In the top right-hand orange box, what I'm trying to highlight here is that the self-attention within the model is really corely focused on the amount of reward that was offered. And in this case, it's not a number, it's not a sum, it's just suggesting that it will be handsomely rewarded, which is an interesting generalization above monetary values. In the second example, the model is attending to the wrong part of the input, but it's still attending to something that's the name of a person. And so it seems like the model can learn something about the meaning of text from pixel-only representations. I'm going to start wrapping up now. I think I have about 4 minutes left. Um, some of the overall insights I want people to take away from this is that it is possible to learn general purpose transferable representations of text directly from render text in pixels without any additional linguistic supervision in terms of tokenization, in terms of other labels that you might have about morphological details. The second is that if you have careful consideration of how to structure the rendering of your text, in other words, kind of like tokenization, this is really important. And what we found was that thinking about how to render the text for the bigram strategy produced much better downstream performance than an unstructured rendering approach. The final insight I want people to take away is that we found that multilingual pre-training without any other architectural changes, so a very carefully controlled experiment, it can improve performance on both seen and unseen scripts. And so I think there's a huge amount of potential for pixel-based representations in the future. So speaking about the future, um, I'm looking ahead for what I think is interesting, not just for pixel models, but for all types of tokenization and tokenization-free language models. The first is, I think we should have a clearer vision of who is the target audience for tokenization-free language models. The really inspirational paper by Joshi and colleagues from ACL 2020 had this categorization of 6 different types of languages, going from the winners at the top all the way down to the languages that are left behind. And I don't know if we should be thinking about people in the winners and the underdog languages when we're thinking about who could benefit most from really flexible tokenization-free models. I also think that we need to think about a better definition of unseen languages. If we are training over really flexible inputs like UTF code points or bytes, what does it mean to be unseen in this space? Is it writing scripts? Is it language families? If it's pixel specific, then it's orthographic similarity. More specific to the research we're doing in Copenhagen, we're going to be focusing on scaling up multilingual pre-training of the models, trying to think about a better understanding of what type of language is learned by these representations, and to develop new methods for building pixel token hybrids. I think there's a really big question here, which is, why is this even possible? We know that masked language modeling in BERT is basically classical distributional semantics, but what is pixel reconstruction? I think this is a really big question. I don't know the answer yet. If you know the answer, or if you want to talk about the answer, please reach out to me. I think this is a really interesting philosophical question. I want to finish here by highlighting some related work that is really exciting. In the same year as the pixel model, we had this great paper by Shannon and colleagues at CVPR on learning an image text contrastive model where the text was rendered into a canvas. It was a really similar idea, super cool work. In 2024, Gao and colleagues worked on improving language understanding from screenshots, where they combined image patch reconstruction and language model prediction using a kind of what looks a bit like a T5 style architecture. The pixology work from Tataria is really nice on trying to understand what type of linguistic knowledge is encoded and learned by pixel models. And more recently, there's some great work on trying to handle suboptimally covered inputs in existing decoder LLMs using pixel fallback mechanisms. And this is by Lutz and colleagues. So I want to thank everyone for their attention. Pixel, which I've spoken about exclusively today, is a really different type of language model that tackles the open vocabulary problem using rendered text. This enables high quality transfer to different scripts, new unseen languages, and different fonts even within existing languages. We can have compact models with as few as 5 million parameters without distillation. And we found that multilingual pre-training improves performance beyond English-only pre-training. So there is a lot further to go here. And it can provide a nice natural interface to working with scanned documents. With that, I will thank you once again, and I'm happy to take some questions.
Great presentation. Early in the presentation, you showed this visualization of the different convolutional kernels. I was just wondering how you attributed the representation in each kernel to the actual visual feature.
That's a great question. Which version of the answer would you like?
I've got plenty of time. Depends how much time
So
everybody else has.
I attributed this by myself. There is no mechanistic explanation of what's happening down here in the model. I think that if we were to compare this to maybe a bigrams strategy, which I haven't done yet, we would find completely different weights within these convolutional weights. But I think that it would be really exciting to take one of these models and to try to maybe think about looking at an SAE or something that we could attach into it to understand what's actually happening, not only at the convolution layer, but deeper within the transformer. So I think the first part of the answer is maybe a disappointment to you, but there's speculation about what we could do here to actually give labels to these. And also, I looked at this a lot myself, and the more you look at the weights of a model, the more you convince yourself of things that are maybe not really there.
Hi, thanks for the great talk. My name's Angelica from SFU. I have a question because I'm very excited about this. I'm a roboticist, so pixels, understanding through pixels is my thing. I wonder, a kind of high level question, how humans process pages of data, pages of text. Do you know about how humans use saccades or, pick out the important pieces from an image of text, and how that might differ when you're learning, you're teaching a kid through, I don't know, pointing at a book and reading with your finger versus the inference part. So you're, learning versus inference. Are there different ways we should be representing it or encoding versus decoding? Sorry, that was a lot, but yeah, thanks.
Thanks for the question, Angelica. This definitely goes outside of my comfort zone. I have never worked with uh, understanding human-based reading of text, but my office mate during my PhD did this. Somebody in the audience probably knows a lot more than I do, but my understanding is from a scientific study perspective, there are two dominant approaches. You either have people read a whole block of text at once, and you track where their eyes look. And in this case, if I remember correctly, and this knowledge is more than 10 years old, things have changed, I suspect. People don't look at every word in the input. They can scan over many of the words because they don't need to directly focus on them. This may be because they can do something based on prediction effects, or it could be because they can see it within their peripheral vision. The second approach would be self-paced reading, where you press a space bar and you see one word at a time, and then you can understand how surprised people are when a word appears in a sentence. Um, and so I guess that I'm not really sure how to connect this back to how children might learn how to read within a classroom or an adult child learning environment. It might give some interesting inspiration for what types of inputs does the pixel-based language model need to encode? Is it necessary to encode everything? I actually think that generalizes a lot further beyond pixels to tokenization-based models. I hope this kind of answered your question, but like I said, I'm not a psycholinguist, and so my knowledge here is a little bit sparse.
I was wondering if you had a viewpoint on how well the pixel-based approach works between like different styles of generative models, BERT, for GPT style transformers and things like that. Fusion
I'm
models.
sorry, could you rephrase your question? I didn't quite
Yeah.
understand.
Well, do you expect that the pixel style, the relative performance between the pixel style approach and the more conventional approaches, you have the same story for each of these different generative models, or do you think that the story changes as you go from one generative model to another, or what?
I mean, my understanding is that the story of, if we're talking about probabilistic generative models, I think there's quite a difference between something like encoder only BERT model and a decoder based GPT style model. Um, and I think that you can develop arguments about what might be happening within tokenization based models because you know what the discrete inputs are. Whereas I think for something like Pixel, it has the full 16 by 16 representation space to work with for each input. It doesn't use all of them. Um, but I think that it's a harder generative model to train. And there has actually, I missed one paper. There was a paper, I think, in the findings of ACL 2024, where they tried to do some post-training of the pixel model using a GAN to force better reconstructions in the model, to control the kind of almost free-spirited reconstruction it does as a generative model in that sense. We've also had some experiments in the group where we tried to train it as a decoder-style language model from the start. This was very difficult. The model quickly just kind of falls apart and wants to predict end of sentence tokens, like full stops, all the time. So that was a little bit frustrating. So there's something that we need to definitely do in that direction. And I think that when you think about tokenization-based inputs, they will have much more success in learning the probability of the next token given all the previous tokens, because all of this can somehow, I think, be discretized within the massive language modeling space, or maybe there are useful subspaces within it. I'm not sure if this answers your question, but I think that your question probably deserves a lot more discussion than we could have here in a few minutes.
Thank you very much for your presentation. And I have a question. Maybe it's not related to your talk, but I just like feel it's kind of interesting. So I heard some claims, but maybe not by linguists, but by some politicians, like some scripts are more suitable for some languages. So say, for example, like there are some languages with multiple scripts using the same time, like say Kazakh, like there are people using Cyrillic, and they're switching to like Latin-based script. But also like in Xinjiang, like the Kazakh, they are using the Perso-Arabic script. Yeah, so basically, I'm kind of curious about like, are is this is this claim like kind of supported by the pixel-based model, or like it's just like nonsense?
That's an interesting question. So the first thing I'm going to say is that this sounds way too political for me to try to answer. I'm a bit scared about how to answer this question, because I think that languages are such a national construct, or not, and also cross-border construct of groups of people. But you raise an interesting point. We actually did want to evaluate Pixel on pairs of languages where we could find both writing scripts for it. I don't think we succeeded. It would be really cool to find different data sets where we could do this for like classification or dependency parsing. It would be exciting to know, is there an advantage of one type of writing script over the other? But then we still have to disentangle whether this is because we have seen a related language during pre-training, or if we're getting some kind of genuine transfer in the representation space. If you want to send me some of the articles you've read about this supposed benefit of different writing scripts, I'd be happy to read them and to take that into consideration. But thank you.